Hi, everybody. In this mini lecture, I thought it would be interesting to think about a different perspective on our solar system, to look at it in different ways and to kind of compare the sizes of the astronomical bodies within our solar system. When we talk about them and look at the numbers, look at the numbers in a table, it doesn't really mean as much as if we take those images and put them side by side and really compare how the sizes of these planets compare to each other and really take a look at their orbits from different perspectives. So that's what we're going to do in this mini lecture. Here I have a NASA simulation of our solar system, and I'm going to link it for you as well. I can use my mouse and sort of drag it around, and I can see the solar system from different perspectives. So here's our sun. We've got all of our planets out to Neptune in front of us. And so what I'm going to do is I'm going to turn it so that we're looking at it from above, okay? Here's our solar system from above. We've got closely packed in there, our inner 4 planets out to Mars. And then we've got Jupiter, Saturn, Uranus, and Neptune. Now let's see what happens when we flip it and look at it from the side. So I'm going to grab it and we're going to look at it from the side. Okay. And we see we're looking down the disk of our solar system. And the majority of the planets in our solar system, lie along this disk, this flat disk. But it's not a perfect disk. There are, the planets have some orbits that are inclined a little bit with respect to each other. But then in particular, let's take a look at Pluto. I don't know if you can see, right here is Pluto's orbit. And you can see how Pluto's orbit is really highly inclined with respect to all the other inner planets in our solar system. And in fact, when we look at it from some perspectives, and if we look at it from above, let me just zoom out here. Depending on how you look at it, if we look at it from above here, about like this, and like also the image in our textbook, and some of you pointed this out in a future mini lecture to me in your notes, that here's Pluto's orbit, and it does pass within the orbit of Neptune a little bit right here, okay? So when you're looking at it from above, you might think, oh my gosh, there might be some point in the future where Pluto and Neptune's orbit are gonna overlap and they might smash into each other. It does look like that when you're looking at it from above, but it doesn't look like that when you're looking at it from the side. So actually, let's take a swing around and look at Pluto and Neptune's orbit from the side. And you see actually right here that when we change our perspective, the way that we're looking at the solar system, we see that actually Pluto and Neptune's orbit, there's enough of a gap right here in that place where they were overlapping from above, that from the side here, we see that there's enough of a gap between those orbits that Pluto and Neptune will never have a point where their orbit intersects. Now, while we're here, let's take a look. So we've got Pluto's very highly inclined orbit. Over here, we've got 2 objects, Makemake and Haumea. These are both dwarf planets. Pluto is now characterized as a dwarf planet. Pluto has this very highly inclined orbit. Haumea and Makemake also have this very highly inclined orbit too. And they're considered to be dwarf planets. So if I click on, I'll click on Haumea here, and we get this little pop-up window. Haumea rotates so fast that its spin has distorted it into a shape kind of like that of an egg. And even though it's a dwarf planet, it also has moons. So this dwarf planet Haumea has 2 moons, and these moons and the planet, or the dwarf planet Haumea, Makemake, they are named for they're named after Hawaiian names. A lot of these dwarf planets are being found with telescopes in Hawaii, and so they give them Hawaiian names. Makemake, for instance, is named for the Polynesian creator god. So you can click on these and learn more about them in this pop-up window here. Now, let's see. Let's take a look at some of these others. Here's a particular interesting object called Arrokoth. It's out here past the orbit of Pluto. If I take a look there, Arrokoth is part of the Kuiper belt, or the Kuiper belt, and you'll learn more about Kuiper belt objects later in a couple of weeks. So this is what it looks like. And it is kind of like an asteroid, I guess. And it's got these two lobes on it. And the way we think it was formed is that these two lobes were kind of maybe originally separate asteroids orbiting each other. And then over time, their orbits brought them closer and closer together because of their mutual gravitational attraction. That's our universal law of gravitation. And then they eventually kind of fused to become one object. And it makes this kind of snowman-like shape, perhaps. And this spacecraft here, called New Horizons, is a spacecraft that is the one that flew past Pluto and got us this beautiful image of Pluto's surface. And it just kept on going, and then it took an image of Arakoth. So now we know what it looks like too. And before New Horizons passed by Pluto, we didn't really know what the surface of Pluto was like. But New Horizons passed by Pluto, and it found that Pluto has mountainous regions, it has valleys, it's got a rocky surface, and it's icy too. It's got a lot of features that are similar to terrestrial bodies in our solar system. Okay, let's look at some of these comets. And so we talked about how comets have very highly elliptical orbits. They have very stretched out, long, kind of oval-like orbits. And you can really see that. We see, you know, here's the sun. Here's Halley's Comet way over here. And, oh, and here, way down here is Hale-Bopp. Okay, so if this is the disk of our solar system, these comets are not orbiting within the plane of the solar system. They kind of swoop in by the sun, but then when they come out to the far reaches of their orbit, that far reach of the orbit may not align with the disk of the solar system at all. Let's take a look at Hale-Bopp here. This comet was very visible in the sky around the year 1997. Some of you may not have been born yet. And it's on a very elongated orbit. So it passed by us in 1997, and it will not return until the year 3731. So that's how quite elliptical its orbit is. Let's see, Halley's Comet is what we call a short period comet. It comes around much more often than the comet Hale-Bopp does. Now I want to take a look at sort of the comparison in size to some of our planets. I'm going to click on Jupiter, and here, oh, let's see, Jupiter has 79 moons. That's a lot of moons. At least that's the number that we know about. It probably has more. I'm going to click down here on compare size, and we're going to see how Jupiter compares in size to our solar system planet. So Jupiter is the largest planet in our solar system. It has a diameter about 11 times greater than our Earth. So here's how Jupiter compares to the size of our Earth. And let's see. Compared to our moon, compared to Mars, Vesta is a dwarf planet. Here we have Jupiter in comparison to Saturn. So Jupiter and Saturn are much closer in size for sure. And I'm going to ask you to compare Earth in size to some of our other inner terrestrial planets. And to do that, you're going to find Earth here, and we're going to click on it there. And then here where it says compare size, you can click on it, and then you're going to get that screen similar to what I saw for Jupiter side by side in comparison to the other planets. And you're going to compare Earth in size to some of our inner terrestrial planets to see how they compare. It's kind of hard to imagine the comparison in size of our planets just when we're looking at, you know, these flat images on a PowerPoint slide. And so I think that this visualization does a really good job of helping us to better understand our solar system from a different perspective. One last thing I want to do is I'm going to click on Jupiter, and we are going to, oh, click on Jupiter. Down here, I'm going to click on Jupiter. We zoomed in close to Jupiter's surface. Right here, this arch that you see passing along here, that's the orbit of a satellite, a telescope called Juno. And Juno is orbiting around Jupiter and taking data about, well, it's taking images of Jupiter's cloud layers, and it's also taking data about Jupiter's magnetic field. Jupiter's has the largest magnetic field of any planet in our solar system. So here we're coming around, we're orbiting around Jupiter at the moment, and we're seeing kind of the shadow that's appearing right here. And as it comes around, this is the shadow of one of Jupiter's moons falling onto Jupiter's surface. And this moon in particular that we're seeing today, this is a real-time visualization of the solar system at this very moment. So whenever you click on it, you're going to see what's going on in space at the very moment that you're looking at this visualization. So, oh, I don't know, maybe my computer's lagging behind a little bit, but right here is a shadow. And that shadow is the shadow falling on Jupiter from one of its moons, Io. At this moment, Io is directly between the sun and Jupiter. And so the sun is shining on one side of Io, and that's casting a shadow from Io onto Jupiter's surface. That's what's happening there. So let's see, we can swing around and I'm gonna zoom out a little bit. Let's take a look at the Jovian system. Jupiter has these 4 large moons called the Galilean moons, and those are Io, Europa, Ganymede, and Callisto. These are called the Galilean moons because Galileo was able to first observe them with the telescope. The telescope that Galileo had was high-powered enough in order to look at Jupiter and see those 4 moons orbiting around. These 4 Galilean moons of Jupiter are named for 4 of Jupiter's, let's say, girlfriends in Roman mythology. All the planets are named after Roman mythology, where Roman gods and goddesses, whereas the majority of our constellations are named for Greek gods and goddesses and those mythology stories. Let's look at the Galilean system from the side. So here we're seeing it from above. It looks pretty similar to what's going on in our solar system. If we look at it from the side, we also see that all of those 4 Galilean moons are sort of aligned in the same disk around Jupiter, which suggests that as Jupiter was forming, it had some extra debris orbiting around it. And that extra debris kind of bumped into each other and built to become planetesimals and grew to become the moons that are orbiting around Jupiter. So the similar process that was happening around the sun to create our planets, there's a similar process that was happening around Jupiter to create its 4 large Galilean moons. At least that's what this suggests. And we can compare the size of Io, which is Jupiter's closest in large moon, has volcanic activity on its surface. That's why it looks a little bit yellowy here, kind of like moldy cheese. Here's Io in comparison to our moon. Io is actually bigger than our Earth's moon. There's Io in comparison to Phobos, which is a moon of Mars. Io in comparison to Ceres, a dwarf planet. Io in comparison to Europa, one of the other 4 Galilean moons. Ganymede, which is actually the largest Galilean moon. And then Io as it compares to Callisto. So I'm going to ask you to play around a little bit with this simulation and try to discover and explore a few things on your own about our solar system.